Welcome to This Explainer. Today we're unpacking the invisible rules that govern absolutely everything around us, from the mechanics of your morning commute, to the physics of professional sports, to why things crash. If physics usually scares you, don't worry. We are going to eliminate that fear right now. Let's break down the logic behind motion.
Okay, let's dive into this. Picture this. You're standing on a moving bus, completely relaxed, maybe just lightly holding onto a rail, and suddenly the driver slams on the brakes. What happens? You instantly lurch forward. It literally feels like an invisible hand just shoved you in the back. But nobody touched you, right? There's no sudden gust of wind inside the bus pushing you. To solve this highly relatable, real-world mystery, we first need to look at the absolute mechanics of motion.
At its core, a force is really just a simple push or a pull, but its effects are incredibly versatile. It can basically do four things. One, it can warp an object's shape, like squishing a bug or crushing a soda can. Two, it can manipulate speed, so speeding things up or slowing them down. Three, it can change direction, like throwing a car into a sharp drift. And four, it can entirely change an object's state, jolting it from rest to motion or stopping a moving object dead in its tracks. Think of a perfectly matched game of tug-of-war. 10 pounds of force pulling left, 10 pounds pulling right, the net force is 0. And this brilliantly illustrates what we call balanced forces. That balance means 0 change in motion, and the rope goes absolutely nowhere. But the moment one side pulls just a little bit harder, say 12 pounds on the right and 10 on the left, you now have an unbalanced force. The net force is greater than 0, one side wins, and the motion instantly changes.
Now, let's take these rules off the planet for a quick thought experiment. Close your eyes and imagine you are floating in deep, empty space. There is no air, no gravity, absolutely no friction rubbing against you. If a fellow astronaut comes over and gives you a tiny, gentle push, would you ever stop moving? The ancient philosopher Aristotle actually thought that objects needed a constant, continuous force just to keep moving. But in our frictionless space environment, that's just not true. If someone pushes you in space, you're going to drift in that exact direction at that exact speed forever.
The reason you would drift forever is due to a fascinating property of the universe we call inertia. And hey, if physics terminology usually scares you, we are breaking it down together. It's just an object's natural stubbornness. It's the tendency of literally every object in the universe to resist changing its current state. If an object is resting, it stubbornly wants to stay resting. If an object is moving, it stubbornly wants to keep moving in that exact same way, until something forces it to stop. This cosmic stubbornness shows up absolutely everywhere, in three main ways. First, inertia of rest. It's why heavy apples snap off a shaken branch. They stubbornly want to stay at rest while the tree moves. Second, inertia of motion, which totally solves our initial bus mystery. Your body just wants to keep moving forward even when the bus brakes. And third, inertia of direction. This is why you get pushed outward against the car door during a sharp left turn. Your mass is just trying to keep traveling in a straight line. Sir Isaac Newton eventually codified these everyday observations into his official first law of motion. Simply put, an object remains at rest or in uniform motion unless acted upon by an external, unbalanced force. So the crucial point is, nothing changes its state of rest or motion without an outside push or pull breaking that balance. But knowing what makes objects move is really only half the story. What happens when those moving objects actually hit something? Let me pose a striking comparison: a tiny bullet fired from a gun versus a massive truck rolling slowly down a hill. Both are incredibly dangerous, but for totally different reasons. How can something so exceptionally tiny and something so huge cause the exact same amount of destruction? The answer lies in a concept called momentum. Momentum is essentially the combined threat level or impact potential of an object. It takes into account two vital things: how heavy the object is, its mass, and how fast it's traveling, its velocity. A bullet sitting stationary on a table is harmless because it has 0 velocity, but fire it from a gun and its extreme speed gives it deadly momentum. Conversely, a truck moving at a crawl is deadly because its extreme mass gives it massive momentum, despite the sluggish speed. When you look at the math, it's elegantly simple. Momentum, represented by the letter P, is just mass multiplied by velocity. P equals m times v. Now, what's really interesting about this slide is that this equation tells a very clear story. If you want to drastically increase the impact of an object, you either need to make it much heavier or you need to make it much faster. Increase either one and the momentum skyrockets. Let's ground this math in a scenario you've probably seen on TV or experienced yourself. Catching a fast-moving cricket ball or baseball. The ball is coming at you with a lot of momentum. If you catch a fast-moving ball with completely stiff hands, the momentum drops to zero instantly, and your palms take a massive, painful beating. Ouch! But professional players don't do this. They pull their hands backward as the ball hits. By pulling back, they increase the time it takes for the ball to stop. Spreading that change in momentum over a longer time safely reduces the force on their hands. This dynamic of stretching out the impact directly informs Newton's second law of motion. Let's move to and see how this builds. He realized force isn't just about the total change in momentum, it's about the rate of that change. The law states that force is directly proportional to the rate of change of momentum. Basically, if you stretch out the time of an impact, like falling onto a soft mattress instead of a hard concrete floor, you drastically lower the force your body experiences because the momentum changes slowly, not instantly. When you take that relationship between momentum, time, and force, it boils down to the most famous equation in mechanics, F equals ma. Force equals mass times acceleration. This simply means that the amount of force applied to an object directly drives how much that specific mass will accelerate. Push a heavy object and a light object with the exact same force, and the light object will accelerate much faster, all thanks to F equals ma. This brings us to the final core concept of motion, and it's beautifully visualized by something as simple as swimming. Think about it. You're in the pool, you're using your arms and legs to apply a forceful action, pushing the water backward. But your body shoots forward. Why? Because the moment you push the water backward, the water pushes you forward with the exact same amount of force. It's actually wild when you think about it, because this is Newton's third law. Every action has an equal and opposite reaction. It is the fundamental law of interaction everywhere in the universe. When a massive rocket needs to go up into space, it doesn't push against the air. It blasts superheated gas downwards with immense force. The action is gas going down, and the equal and opposite reaction is a multi-ton rocket being pushed violently up. Even when you are simply walking down the street, you are pushing the pavement backwards with your shoes, and the pavement is literally pushing you forwards. Force isn't just an abstract concept trapped in a textbook. It is the silent engine driving every movement in your life. Whether you are balancing on a moving bus, catching a fast-moving ball, or just taking a simple step forward, Newton's invisible laws are right there, dictating the outcome. So the next time you drop an object, go for a swim, or step on the brakes, I challenge you to look closely. Which of these invisible forces can you spot pulling the strings in your world? Keep observing, keep questioning, and keep learning.